So thank you very much for the very kind words and for inviting me to give you this introductory lecture. The idea today is to talk about my most recent love and challenging area of activities, which is 3D printing. And the idea is really to show why I feel that 3D printing is a bridge to the future and at the same time is a new research arena, at least for people in Pavia, but I guess for many people here in the audience. And in the presentation, besides talking 3D printing and what we are doing now, I would also like to show you a few ideas, few slides on the fact that 3D printing has been chosen as a strategic research area for the whole University of Pavia for the period 2015-2017. So 3D printing is becoming a very well-known area, but what is 3D printing? 3D printing is also known as additive manufacturing, and it's the ability to create objects through a sequential layering process. So it's a technology from which you start always from a CAD model, so it's always very connected to drawing an object on a computer. And once you draw on the computer, then the second step, you do a virtual slicing. So you draw the object you want to create. Then you slice it on the computer. And then you send it to a 3D printing machine, which creates the object. So this is a first very important concept. So 3D printing seems to be a trivial concept, but 3D printing is highly is a manufacturing technology which is really connected to CAD system. Okay. So in this movie, I show you at higher speed a very simple 3D printing machine. So basically, there is a head, there is a nozzle, which deliver material, and delivering material layer by layer, you can create object. Okay, that's a machine we have in Pavia. This is a small piece that we draw, and once you draw on the computer, so you design your piece, you can send it to the machine, and the machine progressively, slice by slice, produces the object. So this technology is really becoming more and more popular. If you go around and you ask about 3D printing, I guess everyone knows the word 3D printing. And that's also the reason because also very well-known journals are pointing attention to this new technology. And even sometimes they talk of this technology as the third industrial revolution. And that's a very important aspect, and I really believe that it will really change our way of approaching many areas of our world. Usually, to make a kind of shocking statement, I say that 3D printing is not going to be like the internet, which really changed our life, but for sure it will change many things, more than we may believe it. In fact, one of the reasons is the fact that 3D printing is a very general word, but it means at the same time many different things. And here I'm showing you different technology, completely different technologies, which goes under the name, under the umbrella of 3D printing. For example, here there is a first technique, and here it's basically so-called stereolithography. So you 3D print objects starting from a container of liquid polymeric resin, and then there is a head with a light which moves and basically transform the material from liquid to solid progressively, and you can create objects like this. Okay, so you start from a liquid bath, and with the light you create the object, or you can do things which are, approach which are completely different. For example, you have 3D printing which are based on material jetting, which really the same like inkjet printers. So basically the idea is that you have a nozzle, and through the nozzle you spray the material, and the material, once you spray it, it becomes progressively solid, and you can obtain objects like this. Or, again, changing completely the technology, you can have a binder jetting. So here you start from a powder, which is progressively deposited layer by layer. Once you deposit a powder layer, then you spray a binder, and basically the binder glue the powder particles, and you can obtain objects like this, okay? Or you can have the so-called FDM technology. Basically, that's the technology where you have a nozzle with the thermoplastic material. It's the technology I was showing you in the previous movie. Or you can have, for example, the powder bed fusion, where again you start from a powder bed, and you go with the laser, and the laser basically fuses the material which gets, so you start from powder, it's transformed to liquid, and then it goes back to solid. And usually this technology is very often used for plastic, metal, ceramics, and so on. Or you can have also, and that's the last technology I'm presenting, the direct energy deposition, where basically you are melting the material, and then after you melting with, for example, electron beam, then you deposit the material, okay? So why I show you all these technologies? Because all these technologies goes under the umbrella of 3D printing, but you can clearly, I think, understand that with all these technologies, I mean, there are many opportunities, many possibilities, because the technologies are very different for very different materials. So it's a technology which is extremely flexible. And in fact, with 3D printing, you can do many, and that's the most traditional area of application. You can do a lot of rapid prototyping. So you can create very different objects on which you can, for example, you can experience the functionality. You can experience, you know, the aspect of the object, but you can also produce industrial products, you know, like first batch of industrial products to see if they really work. And that, you know, and rapid prototyping was the initial word for 3D printing, but 3D printing is very rapidly moving to the so-called rapid manufacturing. So industries like big companies like Boeing or General Electric are already putting a lot of money on 3D printing, and basically they're deciding that all the batches with the low number of product, like, I don't know, below like 3,000 per year, they are going to produce with rapid manufacturing, with 3D printing. So, so they're approaching rapid manufacturing with 3D printing, and the reason is that it's a very flexible technology, because you can really change materials, you can really change, also there is the connection I was showing you between CAD and the production aspect. So I started to work on 3D printing a few years ago, and I immediately realized that it was such an interesting technology that I want to build a lab. So in Pavia, we start to buy few machines. So we create a so-called proto lab at UniPD. We start to buy a few 3D printers. All these are FDM technology, so they use thermoplastic material. But more recently, we bought also a binder jet technology, a stereolithography machine, and we are working on a very simple bioprinting system. And what we do with this machine in Pavia, we do the standard, you know, we do some activities which are very classic. So we do 3D printing service. So as a service, we produce objects mainly for colleagues. And it's incredible how habilitating is the technology. So how it's easy to produce components and also to develop new ideas with the colleagues. Even with colleagues, you know, in very close areas, but, you know, not exactly your area. In fact, the second activity we are doing more and more is we start from an idea, in general with some colleagues, and then we develop components which are used in experiments which are useful for, you know, to bring on research. So we do 3D printing service, prototyping based on new ideas, and one of the major activities is medical prototyping, which I'm going to talk briefly. So these are some examples of, you know, simple components we are producing in our lab. So we are becoming a lab which produces pieces for our own experimental activities or for experimental activities of colleagues. You can see with quite complex geometry. And the other activity is mainly use 3D printing as a support for surgical planning. So the idea is that we start from CT images, so from images taken from specific patients. We highlight the organ of interest for the surgery. So we extract from the CT the component of interest for the specific surgery, for the specific pathology. Then we slice the object and we send to the printer and we create the 3D printed model, okay? And we give this to surgeons, which usually use it for surgical planning, so really to plan the surgery, and they also use it a lot when they go to the surgery room, especially if they do robotic surgery, because sometimes, you know, with the robotic surgery, basically they use this type of screen where the magnification is incredibly high, and they really navigate inside the human body. What happens is that sometimes they get lost. So if you really use a huge magnification and you navigate inside the human body, sometimes they get lost. So some of the surgeons like to bring this 3D printed piece in the surgery room with themselves, and when they get lost, they remove the face from the screen, from the robot screen, and they see the organ, and they realize right away where they are and where they should go, okay? So it's a very funny activity we are working with many surgeons in London. But why 3D printing is so interesting, and why, as I said before, is my most recent technological law? It's because it's really opened the door to many new areas, and one area is the fact that really there are two words which have always been, you know, very fascinating for me, which are coming together. One word is the structure world. I'm professor, as you well know, professor of mechanics of solids. On the other side, so I look at structures. On the other side, I always looked at materials, and usually materials and structure have been, you know, two close words, but a little bit far away. Now with 3D printing, really these two words are coming together, closer and closer. And that's not strange, because we know that, you know, this is possible. A very classical example is laminate composite. So you have a structure where you can really choose different materials, and you can really play with the materials and make it, you know, create your structure optimizing the material. But with 3D printing, you can change your speed in this technology. And for example, look at this example, which is very simple. This is a very simple element. It simply is an element made of a single material, just with holes. And basically, with 3D printing, you can put in your structure, you can put more holes on this side and less holes on this side. So more holes here, less holes here. So you can have really a gradient material. So you can really design material and structure the way you want. So you start to have a lot of freedom. And this really opens the door to many new concepts and many new possibilities, okay? Because not only you can combine, you know, holes and the bulk material, but you can combine these things in obtaining very complex objects, but you can do many other things. For example, here, and that goes back to another, you know, previous law I had, which is shape memory materials. Because combining classical materials with 3D shape memory materials with 3D printing, you can get to the 4D printing. So here you can see a material which was printed straight. It feels that it has been immersed in a hot bath, and it changed the shape, okay? So these are active material, but active material with a very complex shape. So for example, you can have self-folding structures, okay? So think about sending like an antenna to the space, or you know, some structure on the moon. It would be optimal to have structure which can be self-mounted or folded once they reach the place they want, you know, where they're designed for. Okay, so there are many new concepts which are coming easy to exploit with this technology. And not only in this fancy area, but there is also another area where the 3D printing is becoming more and more popular, which is the concept of printing your own house, okay? There are many areas in the world, China, Italy, Netherlands, where people are looking at this concept, and also in collaboration, also in Italy. I mean, we are doing something in collaboration with the University of Napoli, Federico II. We adapt a big 3D printer which is now able to 3D print concrete, okay? And once you 3D print concrete blocks, basically you can really think about the free-form structural elements, and you can start to design, you know, components. I mean, that's the long-term idea, to design components which are very flexible, very fancy forms, you know, objects like this, and these are ideal concepts, example from the literature, but down here you already see elements which are 3D printed, taken from the literature, okay? So you can, with 3D printing, you can really change scale. You can talk about 4D printing, you can talk about printing the concrete, you can think about bioprinting. So there are many, many things, many different areas which are all connected by 3D printing. So that's the reason, because a while ago, when our rector asked for a new strategic idea for the whole university, there was a kind of public call for the whole university. I proposed a project on 3D printing, and fortunately it was selected as the best project in the university. So now Pavia is really trying to put some effort in this area, and that's a quite complex project which is based on 5 pillars. It's modeling and simulation, because Pavia has a strong modeling background, and also because it has a very clear industrial requirements. It's based on new materials, because as I hope I show you, really material play a huge role in 3D printing. It's based on manufacturing, because Lombardy is a second European manufacturing region, so it's a new manufacturing technology, so Lombardy has a really interest in 3D printing. We are also looking at social impact, because again, it's not only a technology, but it's a technology which is changing the rules. So it's really important to study and understand the social impact, and then we put all the applications just in one pillar. It's a very broad project, it's open to many collaboration, and here you can see a long list of different activities that we are working on. Clearly, the goal here is not to read these activities, but since we are in a computational mechanics conference now, the goal is to show you how rich is this area also from the computational point of view, and I'm going to show very initial activities we are working on. So one first area of big interest is discretization, optimization, 3D printing technology. So here you can see a simply supported beam with the load in the center, and basically you can design trivially this beam. You can design this beam, but made of a single homogeneous bulk material. But you can also optimize the beam and try to design the beam optimizing the internal shape and relying on a material which is made of bulk or empty material, basically. So if you optimize your beam and you admit the height can be, you can change the height of the beam, you end up with this very classical optimization results. Okay, so this is the simply supported beam under this load, which has been optimized in order to reduce the weight of the beam, and clearly you obtain this shape. But the point here is that you're not required to have a structure which is made only of one material, like in this case. So in this case, it's either you have the material, which is the black, or you don't have the material, which is the white. But now, with this technology, you can have really graded material. So you can have, for example, points where you have a bulk material, points where you don't have the material, but you can have all the possibilities. You can have like a 50% of material, 10%, and so on. So if you start optimizing with this, with the possibility of having a graded material, you obtain structure like this. So you can see a very different results from the previous one. And so there is a lot of opening, about optimization technology to bring and to make it work with 3D printing. There is also another concept which is not only the optimization, but also, and that's also in some sense is computational, is the transfer of your result, of your, let's say, fine element results, in terms of a code which can be really printed. Because basically, once you have these results, you really need to produce your component. So there is a concept of how can we transform our numerical result in something you can print, and that's not trivial, and there is a lot of work to do. And also in terms of optimization, for example, here, well, let me show you, let me go a little bit deeper on this, well, otherwise I stay here. And here, there is another aspect in terms of optimization which is really interesting. So here, you see that I optimize this structure, removing the fact that I can have either bulk material or empty material. So I really use a graded material. And when we print it, we obtain a structure like this. So we say that, for example, in this area, in this central area, we only need to have a 10% of material, and we printed using a grid, which is a horizontal vertical grid. But conceptually, you can choose any type of grid. So you can orientate your grid in any way you want. And so there is also not only an optimization, another optimization degrees of freedom, but there is then also issue, once you obtain an optimization form, can you really produce it? Can you really produce it? Can you really 3D print the component you optimize? So there are aspects which are really really important on this. Okay. Another aspect. So optimization is one thing, but there are many, as I was mentioning you, many areas where computational mechanics can be really important. And here, for example, is another aspect, which is trying to come up with structural models which are effective. And here I'm focusing mainly on FDM technology. So it's the technology I was showing you before, where it was the nozzle, and the 3D printing is done with a thermoplastic material. Let me show you. Oops. Let me show you the video. It's a little bit fast, so it's a little bit crazy. But I mean, so there is a thermoplastic that's heated up, and then it's layered, and layer after layer you produce the piece. The idea is are we able to construct and to reproduce the behavior, the structural behavior of this component? So the idea is to really build up a model, a structural model of these components, which are produced with this FDM 3D printing technology. You need to really explore the sintering process, the sintering and bonding process, which is a process active at level of the different filaments. And then not only you need to explore this, but you also need to capture the structural behavior of the whole piece. And you have to consider that these materials, since they're based on these wires which are deposited, the behavior of the material of the components is highly anisotropic. So the idea we are pursuing are different. So we're trying to develop, for example, some model on the sintering at the continuum, more at the continuum level. So we are investigating balance equation, equilibrium balance, mass balance with more advanced constitutive equations than classical equations, to try really to model in a continuum approach the sintering of the plastic which is deposited. Or you can use, simplified sintering model, which again, a very classical model, and this is very open for numerical investigations. But once you have a micro model, you also need to go to the macro model, and either through homogenization or through experimental investigations, you can explore the stress strain behavior based on the different orientation of the fibers. Clearly, the behavior is highly anisotropic. And one thing which is really interesting in my perspective is that this technology is so, let's say, so available nowadays that, for example, we are producing our components, our composite components in our lab. We are testing and we are building our numerical model. So it's also a very habilitating technology because you can really design your experiments in your very simple lab. And once you you understand the anisotropic behavior of your material, then the idea is to go one level up and try to detect, to explore your constitutive equation and then build up your structural model, which is the classical, for example, laminate model, but it's interesting to understand if the classical laminate models are still valid or not. So again, classical concept applied to a new technology, new ideas, new research arena. But that's not all, because there are many areas where there are many interesting areas. Many activities to do. For example, I've been talking about simulation, 3D printing process for plastic, but what about metals? So in metals, that's a very a technology which is coming quite popular. And basically there is a laser beam which hits a powder bed made of metals, and there are many different aspects, many physical phenomena going on. So there is heat conduction, absorption, convection, melting and solidification, and so on. So the concept is, are we able to reproduce these effects at the micro scale, and can we do some simulation? So we start to look, in Pavia, we start to look at the lattice Boltzmann method, which seems to be a very flexible method when you have a fluid problem with a rapidly changing domain. And here is some initial simulation we're running, so you can see two powder grains which are heated up, and basically they get liquid, and then they get together. So these are very initial simulations, but there seems to be a flexible numerical tool for the simulations. And these are based, as I said, on lattice Boltzmann. Usually we are working with Navier-Stokes equation coupled to Fourier equations. And clearly we are testing the methodology. So with standard fluid problems, here you can see a Poiseuille flow in a pipe with an obstacle, and you can see that the method seems to be quite effective and also quite simple to code. And here you can see other numerical simulation we're running, and that's a very interesting example, because this is basically, it's a liquid, so we're solving the Navier-Stokes, and we're just heating up the bottom of this liquid. And so since we are coupling the Navier-Stokes equation with the Fourier equation, what happens is that at a certain point, so the material gets, the heat moves up. At a certain point, you start to have some sort of stability phenomena. So you can see that these, the phenomena are quite complex, and these phenomena are exactly what's happening in the metal printer, because basically with the laser, you have a huge heat in one very small spot. So really gets hot in a very small area, and you can have highly unstable phenomena in a point. Okay, let me skip a few other movies. But again, many other areas of interest. That's a very preliminary slide, but I'm really interested in these activities. That's a collaboration with some mathematicians in Pavia, Elena Bonetto and Carlo Ladina. So the idea is that, this technology, it's really posing some question to the computational community. We are discussing about these problems also at the European level, and the concept is that basically with this technology, you deposit layer by layer, you obtain a piece that you want to use in industry, and you can really produce, without going to building your house, but you can easily produce pieces which are, like 20 centimeter or 30 centimeter, and usually you produce this piece, depositing layer which are around like 20, 30 micron each. So it's really, you have a real dimensional problem. Dimensional means that you produce a piece which is quite big compared to the dimension of the layer you use to build the piece. And when you build the piece, in each single layer you deposit, you have local, very highly nonlinear phenomena, okay? So on one hand, you have a highly nonlinear phenomena which are really localized on small layers, and building up layer by layer, you want to produce a big piece. So it's really a let's say multi-scale problem, really a complex multi-scale problem. So the idea is, and usually these nonlinear phenomena are occurring at the boundary of your domain. So the concept we're trying to explore with some mathematicians, mathematical colleagues, is can we do a limit process, and can we transform our three-dimensional problem with a boundary where you have highly nonlinear phenomena to an equivalent 3D problems where you transform your nonlinearity in nonlinear boundary conditions. And once we do this step on which we're working, then there will be all the issue of the numerical implementation. So again, a big arena for computational mechanics. Besides this aspect, we are also trying to do exactly the same thing in a different way, using a reduced order model. And again, the concept is to simulate this additive process. We are starting really to do the preliminary simulation. So here you can see the goal is to build up a 1D element which goes from here to here, and we are building the progressively this component, adding one element at a time, okay? But every time we add one element, we need to solve a boundary value problem on the domain. So the concept is to have a domain, solve a boundary value problem, then add a new piece, and solve the new boundary value problem, and so on. Having in mind that this dimension in general is much bigger than this dimension. So how can you do this? And the idea we're exploring is to use proper orthogonal decomposition techniques. So the idea is to simulate the adding process at the beginning in a very simple classical way, but let's say to learn what is the phenomena occurring in this progressive adding of materials. And once we learn, using this new, what we learned from the previous simulation in order to really speed up our simulation. So here, I'm showing you, so here I'm producing a bar which has a length of 0.1 meter. I'm producing the bar in 10 times steps, so 10 steps of additive manufacturing, and I'm solving only a simple linear heat problem. But the nice thing is that you can see 10 spikes, and the first 5 spikes are obtained using standard finite element solution, and the last 5 are obtained using this POD technology. So the last 5 are much faster than the previous 5 because I'm using what I learned from the previous solution, okay? And you can see that basically, should be also moving. You can see that basically the solution, the last 5 solutions are not very different from the first 5, solutions. And so we are trying to learn about this different way of approaching the problem. Everything here is very simple because it's linear. We have to extend everything to nonlinear. But, again, it's a learning process. It's a new research arena. But again, many different areas of activities. That's another area. This is a very complex slide. Basically, here the idea is to produce the ceramic components with this 3D printing technology, modeling complex chemical thermal process occurring in the material. So you can really, there are some technology where you can produce ceramic components inducing phase transformation inside your material, and the issue is that you have a big change of the shape of your component. So these are seen as cheap production technologies for advanced ceramic components, but the goal is really to control and to model this big change of shapes, okay? So again, that's another area where we're working. These are the first components we produce in Pavia, and now there is an issue of modeling. But 3D printing is really opening the door to many different things. You can really print different materials, so that's another very instructive slides. But the concept is that, for example, we already in Pavia, we have machines. They're quite easy, to buy machine with different nozzles, so you can print different materials. So for example, you can start printing materials which are not conductive and materials which are conductive. So you can start thinking about flexible electronics, for example, or integrated electronics. And that's again, it's a huge, not only a very interesting technological area, but it's also very interesting from the computational point of view, as well as it's extremely interesting the 3D printing of concrete elements. Here you can see, I was showing the movie, yeah, that's another movie that we obtained in collaboration with the University of Napoli, where you can see that we are printing blocks. Here you can see the first 3D printed beams, reinforced concrete beams. So basically we print the concrete blocks and then we apply external steel, reinforcement steels. And here you can see the first beam that we produce, which is a simply supported straight beam. But thanks to the Neapolitan colleagues, we are getting more fancy. So here you can see the new, the second beams that we produce, which has the shape of the Vesuvio volcano, and you can see the beams with me. And what is really interesting about this technology is that also for this technology, it's a free-form concept, so you can start to design beams with any shape, and then you can think about really producing this beam. Not only you can produce a beam of a very complex shape, but you can start to optimize, for example, how to produce it. So in how many segments you want to produce it, the beam. And once you design how many segments, how do you want to connect these segments, and how do you put the reinforcement? So there are many, I mean, it's for sure it's a long way to go, but the very nice thing is that it's a technology which is really changing the game rules, and this means, from my point of view, that's a bridge to the future and really for sure a new research arena. Okay, thank you.
Thank you very much, Ferdinando, for your nice talk. Questions?
Many concepts, quite fast, but
we have time for, we are moving a bit late, but about 10 minutes. We will also postpone a bit start the work session. Please.
That's one of the big issues. That's the reason, because it was hidden in one of the slides. I say that in our strategic project, we put modeling because Pavia is strong in modeling, but we realized that that's the big industrial requirement. There are some very big industrial requirements today. So today you can buy a machine which produce metal piece of 40 centimeters, big machines, like 1 million euros. And they really use this technology in aeronautics in different areas, but to predict the internal stress is still an open question. It's not easy. It's not easy, and that's a very important aspect, which is not, I mean, you're pointing toward a very important aspect, which is an open question for big companies, for Siemens, big companies. The nice thing on the other hand is that we are doing, I was really fast in the presentation, but what's really fun is that we are really, we don't have a metal printer so far, but we have the plastic printers, which have exactly the same problem in some sense, the sintering, and we're planning our own experiments in our small lab. So it's really nice because you can really do your specimen, your experiments, and your testing. Also because even with the plastic printer, you can control everything. It's a real manufacturing process, which is many opportunities, many difficulties. It's a manufacturing process because it's a really, for example, with FDM, which is the most classical technology, is a real extrusion process. So you control the temperature of your nozzle, you control the speed at which you are pushing the material to the nozzle, you are controlling the speed at which you move with your hand. So it's really an extrusion process. It's quite complex. You can control everything. You can do experiments. You can do many, many different things. And nowadays there are companies which are really knocking on our door almost every day, giving us new materials to test, to explore. So there is a lot of activities on this area. It's incredible. The interest that industries are putting in this direction is just amazing.
I just want to draw your attention to an ancient example of additive manufacturing and civil engineering in the construction of concrete dams, where you put one layer after the other. And it's well known that if you want to simulate the initial state of the concrete dam, you do, this is what is currently done, you do active simulation. So there's no way you can get the initial state unless you simulate the production process. Goes over extra stresses and gravity, and there's no way you can get rid of that. So it's interesting because concrete tanks are
Well studied, I don't want to say well known, but yeah. In fact, I mean, Domenico.
this concrete plant is exactly what you do.
But,
This happened when you build a masonry wall, for example.
yeah, but in fact, I mean, in Napoli, I work with the main person with whom I work is Domenico Asprone, who is a structural engineer, and he always says that additive is very new in the manufacturing, classical industrial area, but it's not so new in civil engineering, because civil engineering, everything has been additive. But that's true. I mean, that's true that in dams it's the same. The difference is not only the internal. I mean, the same. I mean, the internal stress concept is the same. The problem with additive is this larger difference of scales. So it's like in a dam, you don't want to model the single layer of production, but if you would like to model really the pouring of the cement with your machine. So really the scale is even much larger, but that's a very good example. Absolutely.
Thank again,
Stop.